In section 3.2, we're going to be looking at our main concepts of the Rolle theorem and the mean value theorem. Now here's what the Rolle theorem says. If f of a is equal to f of b, so basically you have two y values that are the same, and f of x is continuous on that closed interval, and we looked at that idea of continuous on a closed interval when we were looking at things in section 1, and differentiable on the open interval. And we also talked about that idea of when it is not differentiable, like we saw in section 1. Then there's at least one number c in the interval such that your derivative is equal to 0. So again, key point, it has to be continuous on this closed interval containing a and b, differentiable on this open interval containing a and b, then it is guaranteed to have at least one number such that the derivative is 0. Let's look at why that makes sense. If I have some value a here and b here, and we say that f of a and f of b are equal, so their y values are equal, so horizontally they are aligned. If that is the case, and there is any movement at all on this function, it's not a straight line, horizontal line, and it's continuous, so nothing weird is going on, like an asymptote or a jump or a cusp. Then we can say, for me to go up, I must come down in order to be back over here at this horizontal alignment of y values. Then this value here, we're going to call c, and f prime of x would be equal to 0 at this point. Basically, we could draw a horizontal tangent line at that point, and that makes a lot of sense. Like, you have two horizontally aligned values at a and b, so if you move anywhere up or down, you're going to have to come back up or down to get back to that value, therefore creating a maximum or minimum. So if we look at this, it says find the x-intercepts of the function and show that the derivative is equal to 0 at some point between the x-intercepts. Well, let's identify what we're looking at here. Is the function continuous? Well, let's look at this function here. This function is continuous. It is a quadratic. It's a U-shape, a parabola. It's one of our parent functions. We know that it's continuous, and we know that it's differentiable. There's nothing weird going on in that problem that's going to cause us issues. So if we're thinking about a U-shape and we're finding the x-intercepts, this is where y is equal to 0. So we know they're horizontally aligned, so we've got to have some value of a minimum or maximum between the two. And so in order to find our x-intercepts, we're going to backtrack a little bit to algebra days, and we say x squared minus 3x plus 2. We set that equal to 0 and solve it out. So I'm going to factor that. That gives me x and x. The back sign is positive, so that means they're both going to be negative. And what will multiply to give me positive 2 and add to give me negative 3, that's going to be a 1 and a 2. Then I'm going to draw my t-table here, and I'm going to say, well, x minus 1 could be 0, so that would be 1. And x minus 2 could be 0, so that's 2. So those are my two x-intercepts. And if I were to take f of 1 and plug it back into my equation, that would give me 0. If I were to take f of 2 and plug it back into my equation, that would give me 0. Therefore, from Rolle's theorem, and Rolle's theorem is a good test question for me to give, if f of a is equal to f of b, then f prime of c is equal to 0. So we have found the x-intercepts, and we're showing that f prime of x equals 0 at some point in between them. So let's find that point. Let's take the derivative. So that gives me 2x minus 3, just applying power rules, set that equal to 0 and solve. That gives me 2x equal to 3. So x is equal to 3 halves, and so this would be at the value 3 halves, comma. We're just going to plug in 3 halves into our original function, and that should output you a value of negative 1/4. And so that means we would have a value of 3 halves, the point 3 halves, comma negative 1/4, and that would be that point between the two x-intercepts where the derivative is equal to 0. Let's do another example in a different kind of function. This one says, Let f of x equal x to the fourth minus 2x squared. Find all values of x in the interval such that f prime of c is equal to 0. So first we need to figure out, does this satisfy Rolle's theorem? Because the other problem we were looking at were x-intercepts, and x-intercepts are on the x-axis, so we know that they're horizontally aligned. So let's look at this one and see if this one, we want to see, does it satisfy Rolle's? So part 1, is this function continuous on the closed interval from -2 to 2? Yes, it is. This is an x to the fourth function, so it's real similar to your quadratic function, especially in its end behavior. There's no division by 0 or square roots of negatives. There's nothing really funny going on with that one. And step 2, is this differentiable on the open interval from -2 to 2? Again, similar conversation, but it is differentiable. Step 3, and this is how I would want a test question played out, is f of a equal to f of b? Well, let's figure that out and see. Is f of -2 equal to f of 2? So I'm going to take f of -2 and plug it into my function. That would be -2 to the fourth minus 2 times -2 squared, and that gives me a value of +8. I'm going to take +2 and plug it into the same function, and that also gives me a value of 8. So yes, f of -2 is equal to f of 2. So we have satisfied these 3 conditions, so Rolle's is going to apply. I wanted to check that first, because if Rolle's doesn't apply, then I cannot find f prime of c equal to 0, or I cannot find all the values of c where that is true. So now I'm going to find f of x equal to, take my derivative, 4x cubed minus 4x, and I'm going to say it equal to 0. Now they have a GCF of 4x, so that would give me x squared minus 1 equal to 0. And I could further factor that by the difference of 2 squares, so that would be +1 and -1. Now that I have it factored out, I can apply my 0 property, so 4x could be 0, so x could be 0. X plus 1 could be 0, so x could be equal to -1. X minus 1 could be 0, so x could be +1. Make sure you don't forget the 0, 1, and if you had stopped here and not factored it all the way out, make sure that when you did your square root, you got your plus or minus with it. You could have had just, oh, let me let x squared minus 1 be 0, so that gives me x squared equal to 1. But when you square root the 1, it gives you plus or minus 1. So again, don't forget you're getting 2 zeros from that. So this tells me the values of c that are in that interval where the derivative equals 0 would be at 0, -1, and +1. So that's your Rolle's theorem. It does have those 3 qualifications it has to meet before you even want to dive into the derivative. Here's the other theorem of this section we want to look at. The mean value theorem. It says if f is continuous for a to b and differentiable on the open interval, so look at things we already are seeing again. It's continuous on the closed interval, it's differentiable on the open interval, same as Rolle's. Then there exists at least one c between a and b so that the tangent line at c is parallel to the secant line through those points. So this is beyond just having f prime of x equal to 0. It's a matter of it being parallel to the secant line. And remember, secant is just the slope between those 2 points. So this implies that there is a point in A to B where the instantaneous rate of change is equal to the average rate of change. And so here's what that looks like. A and B in this one do not have to be equal. So if this is, switch colors, if this is your A and this is your B, and say A is here and B is up here, they're not that horizontally aligned, we had to have some more qualifications for it, or we had to change up our description. It says, if you have a point here, here is its tangent, and that is going to be parallel to the secant between A and B. And so that means f prime of c is going to be equal to f of b minus f of a all over b minus a, or your slope formula. Because remember, average rate of change was just your slope formula, but it used your function notation as you went. So in your Rolle's theorem, your a and b have to be horizontally aligned and your derivative is going to be equal to 0. But in your mean value theorem, mean value, average, your instantaneous rate of change, or f prime of c, is going to be equal to the slope between a and b. So we're going to have to do a little bit more computations with these. So let's look at this example here. It says given f of x, given f of x equal to 5 minus 4 over x, find all the values of c in the interval from 1 to 4. Be careful with this because it is open like this. Make sure you know that's an interval notation. That's not an ordered pair. Such that the instantaneous rate of change, that's going to be your derivative, is equal to the average rate of change, and that is your slope formula. So it didn't flat out just tell you to use mean value theorem, but it is giving you these words to help you. So here's what we need to do. First, we need to say, is this function continuous? Yes, this is continuous on this interval from 1 to 4. It would not be continuous if it contained the value of 0, because 0 right here in the denominator would cause us some issues. But we are continuous 1 to 4. Are we differentiable? Again, we would have issues if 0 was included in there, but since it's not, we're also differentiable. So since we know those two things, the first thing we need to do is we need to find the average rate of change, and that is the slope between our two endpoints at 1 and 4. If I'm doing that, I'm going to have a little bit more information. I know 1 is the x value, and I know 4 is an x value. And so I need to find out their corresponding y values. So I'm going to say f of 1, and I'm going to plug it back in there into the equation. 5 minus 4 over 1, that gives me 1. So now I have the ordered pair 1, 1. F of 4, so I'm plugging 4 back into that original equation. That gives me 5 minus 1, which is 4. So I have the ordered pair of 4 over 4. So now if I do my slope between these 2 points, I'm going to say y minus y over x minus x. That would give me 3 over 3, which is just a value of 1. Now that I found the average rate of change, I'm now going to find my instantaneous rate of change. And that would be dealing with my derivative. So I'm going to say f prime of x is equal to, now f of x was equal to 5 minus 4 over x. So I'm going to go ahead and apply my algebra. That would be 5 minus 4x to the negative 1. So that when I take the derivative, that would just be, let's see, I would bring the 5's derivative to 0. So I bring the negative 1 down, and that would make it positive 4x to the negative 2. So 4 over x squared. And so I want to take this average rate of change, set it equal to this instantaneous rate of change, and use my mean value theorem. And so step 3, finally step 3, from the mean value theorem, I want to set 4 over x squared equal to 1. So in order to solve this out, I'm going to multiply both sides by x squared to cancel it. So I get 4 minus x squared, 4 equal to x squared. I'm going to square root both sides, and so that gives me x equal to positive and negative 2. But remember, we're in that interval from positive 1 to 4. So really, it's just going to be at the value of x equal 2. So at the value of x equals 2 is where I would have a tangent that is parallel to the average rate of change between my endpoints, like we saw here in our picture. Now, why do I like the mean value theorem, and where you're probably going to see it on the test? I really like this question, this police officer question. It says a driver passes a police officer while traveling at 55 miles per hour. All right, good citizen. 4 minutes later, the driver has driven 5 miles and passes a second police officer while traveling 50 miles per hour. All right, we're not speeding again. Prove the driver must have exceeded 75 miles per hour between the two police officers. Oh, so we are just following the rules when we see a cop. I know no one ever does that. And so we need to make sure that did this person exceed the speed limit? And so I always love a good picture to figure this one out. So let's kind of draw this out from here. So right here, someone is going 55 miles per hour. 5 miles later, they're going 50 miles per hour. You think, oh, they slowed down some. Well, in that 5 miles, we're wondering, did they exceed that speed limit or exceed at 75 miles per hour? We'll call it the speed limit. Well, this we're going to call time equal to 0. So if 5 miles later, it said was 4 minutes, well, we're in miles per hour, so 4 minutes later would be like time equal to 4 over 60, so 1/15 of an hour. This gives me an ordered pair of 0, 0, talking about time and distance. This gives me an ordered pair of 1 over 15, 5 of time and distance. And so by the mean value theorem, the instantaneous rate of change is equal to the average rate of change at some point between 0 and 1/15, because 1 over 15, because it was continuous. He didn't just jump off the road and jump onto another road, whoever it was. And so what I want to do is I want to look at my derivative, and I'm curious. That means my derivative at some point of that function would be equal to the average value, so I'm going to find slope, 5 minus 0 over 1/15 minus 0. That gives me a value of 5 over 1/15, which is equal to 75 miles per hour. So the average rate of change was 75 miles per hour. And by the mean value theorem, the instantaneous rate is equal to the average rate at some point between 0 and 1/15. So for him, her, whoever it is, for them to go 5 miles in 4 minutes and to be clocked at 55 and 50, the average of their speed was 75. That means somewhere in between here, they hit some point of 75. And so this person did exceed that. And so really interesting on how that mean value theorem can go into the speeding and how far we have gone and how much time it's taken us to get there. Now, this one didn't have a function. We weren't taking a derivative of any given function and plugging a value there. We're not trying to find the exact point that they hit 75 miles per hour, but you can see the application behind it. And so this is a nice problem that you're going to see possibly in a testing situation. And so I hope this helps with those two theorems in 3.2.